Hi, and welcome again to the XEGB Tech Talk on the V-Hub, or the Variable Pitch Racing Fan Hub. I'm Rich Worthy. In this section we'll be looking more at the construction and assembly and the testing of the actual hub. In the first part we looked at the theory behind the variable pitch hub and why it's an advantage, and the design stage. So let's move on. I'm not going to dwell too much on the manufacturing of each individual component. The V-Hub was designed to be made in a home workshop environment, not needing any fancy kind of CNC or 5-axis milling machines. But it was an advantage to get some of the aluminium already profiled using a water jet profiling company. You can see there on the left some of the components, the star plates, the blade paddles. They were water jet profiled to a very high accuracy, which saves a lot of work and effort. The only other thing you're going to need, even in a workshop at home, is a lathe, but nothing fancy. Mine's an old Imperial benchtop lathe. You can see on the left hand side there there's a blade clamp in a jig assembly. That means you can get repeatability and accuracy each time. Here you can see all the components of the V-Hub spread out on the table. There's maybe over 140 different parts there. You can see all the blade paddles and the clamps, from the drive hub up to the stub shaft. Everything there that makes it up. Now people say, how heavy is it? Well, when you consider the rotating mass of a normal 12 blade multi-wing fan unit on a hub, it's about 4.7 kilograms. This one's just over 6, so it's about 1.5 kilograms more weight, but it's still a big advantage to have. When we start to assemble the V-Hub, we start off with the blade paddles and the star plates. You can see in the top right hand side there, you can see the spherical bearing in a taper threaded sleeve that I made for them, and that then gets screwed into the blade paddle and locks in there on its taper thread. This is to resist the sideways motions of the spherical bearing as well as the centripetal motion. Now when you fit those to the star plate, it locates onto spigots which are inset into both sides of the star plates. These are hardened grade 8.8 steel spigots with a shoulder on, so that when you clamp the actual assembly together, the spherical bearings aren't pressing into the aluminium, which would soon wear. You can also see a little O-ring on each one, which is forming a seal. And there, when it's fitted, you can just see a little bit of movement from side to side, which allows the blade pedal to twist. Then you move on to the second star plate. You can see that I've already fitted the spider underneath, which bolts into the sides of each blade paddle. And again, these are fitted on top with the spigots, and through the spigots is a 6mm high tensile socket head bolt. And all that does is clamp the two together. The actual shear force of the centripetal force is taken up by the hardened spigots and the spherical bearings themselves. Here we have the shaft. You can see the hydraulic sleeve there at the bottom, which is, like I said, an annular shape. It's got an inner and outer seal. And the hub slides down this chrome hardened shaft. Quite a nice fit. Straight onto the actual bearing. It's onto the piston assembly itself. Now fitting the hub then onto that, you can see I've already fitted the end, the return spring and the end bearing and adjustment nut. Now in this configuration, if that was fitted to the fan frame, you could bolt either a standard multi-wing type fan on there, or you can fit the V-Hub on there, so you could run with either one. But when we put the variable hub on, the V-Hub, it just fits over the top, 6 bolts into the drive hub and 6 bolts onto the rear bearing, and it's fitted. The last part is to actually fit each blade, and again, using the blade clamps, they all fit just as you would with a normal blade, clamp from either side, and you can adjust the blades then to get a fine adjustment, and the whole unit then is complete. The complete V-Hub assembly bolts onto the fan frame. I do this for a number of reasons. One, you can shim and adjust the actual fan to the duct and to the pulley below, but also if the fan frame gets damaged or you design a new frame, you can swap over the stub axle without any real issues. You can see here the belt fitted to the pulley. Now when the pulley is slightly moving that 5mm backwards and forwards, the belt isn't affected at all. It just follows its straight line as it normally would do, so there's no issues there. And you can see the hydraulic line fitted there. It's a single acting hydraulic line. You can see the tap on the top. That's a bleed tap to at the highest point of the hydraulics to get any air out of the system, and that unit then is ready to go. So how do we know that the V-hub is strong enough to resist all the forces and loads that's imposed on it? Well, there's three forces really that we need to consider. First of all is the centripetal force, which is the throwing out force of all the components, not just the blades but all the blade paddles and clamps. They want it to throw themselves outwards towards the duct edges, and we've got to contain that in. The second one is the bending moment of the blades. Effectively, this is produced by the thrust. If you're pushing out backwards with 100 kilograms of force, it's effectively like pressing on the back of the blades with 100 kilograms. It's trying to bend them at the root and snap the blades off. And the third force is the axial twist. It's the blades themselves not wanting to do any work. They want to flatten off. They want to go easy. They don't want to do any work. So these three are the forces that are acting on it. By far the biggest one is the centripetal force, the throwing out force, and that's the one really that we have to be regulated and measure against. There is a fourth thing that we have to consider, and that's the stored energy that's in any of these components should they break loose and try and break out the duct or guarding. This stored energy is a combination of its mass and its velocity. All these are governed by the WHF regs, and I'm going to show you next how we go about resolving that. So how do we do this? How do we know that these components are strong enough? Well, first of all, you've got to do a few measurements on the actual component itself. For the centripetal force and also for the kinetic energy, we need to know its centre of gravity, its centre of mass. You do this simply by balancing it on a seesaw and marking out from the very centre of the hub exactly where it is. And you can see here that I did it for various combinations of the hub. I did it for the blade itself, I did it for the hub with just the clamps on, I did it with the hub with the blade paddle on, all the different combinations. And by far the weakest point is the connection from the clamps to the actual blade paddle, as you can see on that arrow. So we take a measurement of the blade plus the clamps, and you can see that its distance from the centre of the rotating mass is 0.242 metres or 24.2 centimetres, about 9.5 inch. We also have to weigh this assembly, and we get an exact mass for that, which is 489 kilograms. So we can take these two measurements and we can do a little bit of maths with them. Now I'm going to run you through this. It's dead easy, and that's why I colour coded it. First of all, we need to know how fast that centre of gravity is rotating around. So if you take a fan that says it's usually running about 3000 RPM, we need to put the radius, which is our 0.242, into a calculation, and it comes out with 76 meters per second. So it might be that the tip speed here at the tip is doing 160 meters per second, but around about here, where the actual centre of mass is, it's only doing about 76 meters per second. Now, using that velocity, we can then work out the centripetal force, which is the next one down, which is mass and velocity squared over its radius. So you can see again, it's the mass, which is 0.489 grams, or kilograms I should say, and times by its velocity over its radius. And that gives us a force, an outward throwing force of 11,671 newtons. Now, most people don't know what a newton is. It's a bit of a funny one. It's a unit of force, but we can convert that quite easily into tons. And it's about 1.19 tons. Let's call it 1.2 tons of outward throwing force. Now that's fairly standard for a blade, depending on what RPM it's running at. Also, we can use those two same readings, those two same measurements to work out its kinetic energy, which is half mv squared. So again, it's using that same mass, it's using that same velocity squared, and that comes up with 140 1,412 joules. Now, what's a joule? Again, it's a measurement of energy. Now, we can read straight from the regulations that for our first type of containment, you need 1850 joules. So we're well below that, and so from that point of view, it's past its containment. We don't have to go to any heavy containment in the duct and the fan guarding. But with the centripetal force, we still need to do a little bit more. This is theoretically telling us what actual forces are acting on it under operation, but how strong is the actual assembly itself? We need to know that it beats the 1.2 tonne. Well, we can do that by using a pulling rig. This is something that I made a few years ago. It's got a 60 tonne hydraulic jack, and it uses a 12.5 tonne strain gauge to pull any fan hub assembly and blade assembly to destruction. We need to know its breaking point. So what we're going to do here, if you can see on the right hand side, there's a digital readout on the gauge. It reads 0.000, looking from the top down. Now that's in tonnes, so we're looking to beat 1.2 tonne. Now regulations say an individual component like a blade or even a blade clamp it should be 2 times that. And most multi-wing and Hascom blades break about 2.3 tonne. That's an average breaking strength, so they're just over 2. But if it's a star plate or a main hub, it's got to be 4 times, because you could have the influence of blades either side of it. So it's got to be 4 times the actual theoretical pull, which would make it 4.8 tonnes it's got to resist. So those are the 2 main figures that we're looking at. So let's start the pull test now. Let's see how we get. So it's it's hydraulically operated via hand pump, and you can see that the readings are already going up. So it's already hit 1 tonne now. It's already hit 2 tonne. So we're already reaching that first stage. But now it starts to slow down and putting more force on. And so what we're looking at is the braking force, and we've just gone up to 3 tonne. 3 tonne is still climbing, so we're looking for that magic 4.8 tonne. Now there doesn't seem to be any deformation showing yet. We're going to the 4 tonnes now, so we're literally getting there. So we've hit 5 tonne now, so we're over our limit. But what's it going to actually break at? So we're at 5.5 tonne now. It's getting up to, will it make 6 tonne, you think? Yeah, we're into 6 tonne, so this is well above any regulations required. 6.4, 6.5, 6.6, 6.7, we reached 8. There, it's just broken. 6.89 tonnes. So it's beating the regulations, but let's see what that means. You can see on the photographs exactly where it's broken. It's where the blade clamps bolt through the blade paddle. You can actually see on the top of the photograph where it's broken through where the bolt is. It's because of the reduced cross-sectional area of the material at that point. And at the bottom, it's then levered that out and snapped on an internal corner on a stress point. This is was a known weakest point and designed to be so. It's still a lot stronger than the blade, so in any kind of impact, it's usually the blade that will snap. It's very rare for this to actually happen. In fact, most multi-wing or has-contact cast hubs I've tested usually break around about the 5 tonne mark, which is a lot less than this one. Some as low as 3.5 tonne. So I'm still very, very pleased with this. Using this test result, you can do a ratio between the theoretical and the actual measurements. And you can see that at the bottom, you can put the 6.89 tonne over the 1.19 and you get about a 5.8 to 1 ratio factor of safety, which is a lot more than the 2 to 1 for a single component by the regulations, or even the 4 to 1 for a combined. So it's well above the regulations, so that's passed okay. I did similar tests for the star plate and for the paddles, and I couldn't actually break them. I got up to past 9 tonne, and the rig itself started to buckle. So as of yet, they are unbreakable. With the test results proving the V-hub strength and capabilities, we were starting to do an actual operational test. So the V-hub was assembled into the craft and taken to a nice quiet spot, where we could do things such as test the operation of the hub, both static and under RPM, under load. And you can still see that that test on my Facebook page, which is Crossblades Racing. And we were checking for things like vibration and balance, good feedback and no oil leaks, these kind of things. It performed very, very well. This is a recording of the V-Hub's first full throttle test run. And you can see when I'm operating the lever, the actual physical effects it's having on the fan. It's actually slowing down and speeding up the fan as the load goes up and down with the blade pitch. Then on to the last race meeting of the 2019 series at Magnolls. Took the craft there more to prove its operational capabilities and to drive competitively, but the craft operated exceedingly well. The RPM range changed by about 700 RPM from maximum pitch to minimum, which is exactly what I wanted to counteract the right hand stalling and the left hand overrunning. It allowed me to practice using it in racing conditions, which became very natural and very predictable. And also it was to gain the confidence of the scrutineering committee to aid the passing of it from a regulation point of view. So thanks for watching this Tech Talk on the V-Hub. Hope you've enjoyed it and maybe even learnt a bit of something. I welcome any feedback or comments you might have, and hopefully when we get back out there racing, we'll see it in action. Thanks very much.